Alright, hello class. In this video we're going to be continuing our discussion about section 2.5, which is on subsequences, and today we'll actually get to the Bolzano-Weierstrass Theorem. Of course, this is definitely one that I abbreviate as the BW theorem. Okay, so the first thing I want to start with is what I hinted at last time, was essentially that if a sequence converges, then all of the subsequences also converge to the same limit. Okay, so this is given as theorem 2.5.2 in the book, and it basically says that if a sequence AN converges to A, then every subsequence of AN also converges to A. This isn't too difficult to prove, really. Mainly because if we let epsilon be greater than 0, then there exists a capital N in the naturals such that the absolute value of AN minus A is strictly less than epsilon for all little n greater than or equal to this capital N. Okay, so for any subsequence, we'll call it A sub n sub k. How it actually is labeled. So if you remember, let me shift over here. If we have our sequence A1, A2, A3, A4, A5, okay, our subsequence would be something like we would take A2, but that would be like the first term of our subsequence, and then we might take A4, which would be actually the second term of our subsequence. So for any subsequence, the value n sub k is greater than or equal to k, basically for every k in the naturals. Okay, so thinking about it now, I don't think I explained it very well over here. So in other words, if this is our original sequence, okay, and I create a subsequence and I start here, well, this is, I'll call it S. This is the first term of the subsequence. Okay, and the actual first value here, this 2, it's greater than the 1, right? So this label is, or this index, this A sub 2, that 2 is greater than the 1, which is, this is the first term. All right, now this is the second term, but the actual A index is greater. So A's index here is 5. Okay, so the index 5 is actually greater than the actual index from the subsequence. Okay, so every term of the subsequence, when it's indexed, okay, is greater than that same number in the how we're indexing it in the subsequence. Okay, so what this basically means is that even if you don't follow all that, I know it's kind of working with these subsequences is kind of tricky, but this means that we can use the same n and that's capital N, for the subsequence. Because essentially, since for k greater than or equal to n, the n sub k will also be greater than or equal to n. And so the a sub n sub k minus a will also be less than epsilon, implying that a n sub k, that subsequence, also converges to a. Okay, so as I mentioned before, in actual examples, I think everyone kind of gets a sense of what a subsequence is. When using them in proofs, they can actually be kind of tricky just based on the way that we have to index them and label them. Okay, now the best part about this, so I think this theorem feels obvious, right? If a sequence converges, then all of its subsequences must also converge to the same thing. What's great about it, though, is when we take the contrapositive, it actually gives us a really nice way to show if a sequence diverges. All right, so the contrapositive basically says that if every subsequence basically does not converge to A, then the sequence A does not converge to A. So, in other words, and I'm going to rewrite it, but the contrapositive, I'll just say, gives us a criterion for divergence. Okay, so here's the divergence criterion. Okay, so given a sequence AN, if, well, we have two possibilities. One, if AN has two subsequences, that converge to different values, then AN diverges. In other words, if the limit of AN sub k does not equal the limit of, say, another subsequence AN sub j, then this implies that AN diverges. Okay, or two, if, I already have the if up there, if AN has a single subsequence that diverges, then the original sequence A sub n diverges. Okay, so right here, this one, part one, is probably the easier one to utilize, but this one's also important too. So basically, if you have a sequence and you want to prove that it diverges, one quick way to do it is to just show that it has two separate subsequences, one that goes to one value and one that goes to a completely different value. Okay, I'll show you with an example here. All right, so for example, if we have the sequence, let's say an is, let's say 1/2, -1/2, 1/2, -1/2, 1/2, -1/2, 1/2, -1/2, on and on and on. So it's just plus and minus 1/2 over and over and over again. Well, note that if I just take the even values, 2k, so this is a subsequence, and the even ones will be -1/2, -1/2, -1/2 over and over and over again. So a sub 2k converges to -1/2, where on the other hand, if I take the even values, or excuse me, the odd values, I'll instead get the positive 1/2 over and over and over again. So the odd terms converge to 1/2. So this tells me that an diverges. Right? So an diverges since well, I'll just say the limit of a sub 2k does not equal the limit of a sub 2k minus 1. Right? The limit of the even terms does not equal the limit of the odd terms. Therefore, the sequence diverges. Okay, so this is a much quicker way to try and show that something diverges versus trying to reverse the epsilon definition of convergence. Okay, so this brings us to the Bolzano-Weierstrass theorem, or the BW theorem. And this is an extremely important theorem. It's actually very powerful, because what it says is that every bounded sequence has a convergent subsequence. Okay, so we established early on in this chapter that every convergent sequence is bounded, but being bounded is not enough to make sure you converge as a full sequence. However, if you're bounded as a sequence, you must have at least one convergent subsequence. So while the total sequence may not converge, we can pull out a subsequence that will. Okay, so i.e., if an is bounded, okay, it may not converge. But we can always find a subsequence, a sub nk, that does converge. Okay, to give you an example, if my ANs oscillate between +1, 0, and -1, kind of like they act like, say they act like sine. They just oscillate back and forth. So this sequence definitely diverges, right? AN diverges, but is bounded. Now, if I go through and just grab the peaks and make that my subsequence. So let's make this my first subsequence. I'll call it A sub 1k. Okay? And this one will converge to 1. So there is the Bolzano-Weierstrass theorem in action. I can just grab the peaks, or I could grab the valleys. And I could say this is A2 sub k, which goes to -1. And I could grab the midpoint as my sequence or subsequence. And this would be let's call it 3 sub k. Okay, so this is now another subsequence that converges. So I was able to take or create 3 subsequences here that converge out of this bounded sequence that does not. Now, these aren't the only ones. I could oscillate for a while and then just do zeros, right? So I could grab this sequence, say it oscillates and then does this, and then it just stays here at 1. So this A sub 4 k will go to 1, even though it acts strangely. So this sequence actually has like an infinite number of subsequences that will converge, but the only possibilities are subsequences that converge to 1, subsequences that converge to 0, and subsequences that converge to -1. Okay, so this is the Bolzano-Weierstrass theorem in action. If a sequence is bounded, it may not converge itself, but we can definitely find a subsequence in there somewhere that does converge. All right, so let's prove this. All right, so this isn't the easiest thing in the world to prove, which I'm sure you can imagine, but here's the idea. Let me make my number line a nice color. Okay, so our sequence, we're starting with a sequence that's bounded. So we know A sub n is bounded. So that means there's some m greater than or equal to the absolute value for all n in the naturals. So I'm going to set up an interval from -m to m. And since the sequence is bounded by m, I know that every term of the sequence, an, lives in here somewhere. Oh, and I didn't label this, but this is 0, by the way. Okay, so I know that, the sequence, it may converge, it may not, but it's in here somewhere, right? All of the terms. So an infinite number of terms of the sequence live here. Now, here's how the theorem works. Let's say that we have to have an infinite number of guys here, even if the sequence doesn't converge. At some point, there's a whole myriad of. So let's say that right here, there's just an infinite number of terms. Okay, so here's what we do. And it may not converge because, again, they may every other term pop out and put a point here. Right, so it may not ever be that the sequence settles down in here. It may be oscillating back and forth between these two, or between all these values infinitely. So it never actually converges or settles down. However, because there's, say, an infinite number of terms here, we can actually create a subsequence out of this that will converge. So here's how we do it. First thing we're going to do is we're going to split this interval in half. and pick the half that has the infinite number of terms. So I'm going to call that I1. Okay. Then I'm going to split this interval in half and choose again the piece that has the infinite number of terms. So that would be here, I2. So I'm going to take I1, and then I'm going to take an element A from my sequence in here. Then in my I2, I'm going to take another element from my A's and grab that. Then I'm going to do it again. I'm going to split this into two and pick this side that has infinite number of terms. Now, in this case, both seem to, but I'll just pick one of them. I'll say this is I3, and then I'll grab an element from this interval and call it AN3. And we just continue this process over and over and over again, and continue choosing the side that, or the half of the interval that has an infinite number of pieces from the sequence, and continue that way. Now, if this kind of looks familiar, what we're creating is nested intervals that are closed and bounded. So we're going to actually use the nested interval property in our proof here. And so as we shrink this down, right, and we keep making it smaller and smaller and smaller, it's going to get closer and closer to some x value that we know has to be in every one of these intervals because of the nested interval property. Okay, so this is the idea of the proof. Like I said, it's a little complicated. Okay, but we're just going to work through this idea in a bit more formal way. Okay, let's start. So we're going to start by supposing AN is bounded. All right, then there exists a capital M strictly greater than 0, such that the absolute value of A sub n is less than or equal to capital M for all little n in the naturals. Okay, this implies that each A sub n is in the closed interval -m to m for all little n in the naturals. So for every A, it lives in this closed and bounded interval. Meaning there are an infinite number of terms of the sequence in this interval. So I'll just say i.e. there are a countable so I'll just say there are a countably infinite number of terms of A sub n in the closed interval -m to m. Okay? So now, split this set into half. So consider the intervals -m to 0 and 0 to capital M. One of these must also contain an infinite number of elements. Actually, I should probably call them terms, not elements, because it's not a set. an infinite number of terms of a sub n. Okay, so call I sub 1 this particular set. So the interval containing the infinite number of sets. So call I1, I'll just say this interval. Okay. And choose an1 in I sub 1, which we can do because I know I sub 1 has an infinite number of a sub n's, so I'm just taking one of them and indexing it with a 1. Okay, then cut I1 into half, and let I sub 2 be the half with an infinite number of terms from an, and choose an2 in this I2. Okay, and continue this process. So continue this process such that I sub n is the half of I sub n minus 1 with an infinite number of terms, of a sub n, the sequence a sub n, and choose, and I probably should have used a different letter here, so let me do that. Let me call this I sub m and m minus 1, and so we'll choose a sub m n sub m in I sub m. Huh. Okay, so by definition, I1 contains I2, which contains I3, which contains I4, on and on and on and on. Okay, and each I sub m is closed and bounded. So, by the nested interval property, we know that this intersection, let's say k going from 1 to infinity of I sub k, is non-empty. Okay? In other words, there exists an x in I sub m for all m in the naturals. So there's an x, there's a value x that is in every single one of these intervals that we have created. So if I scroll back up to the picture, as I'm getting smaller and smaller here, like as I said, there's an x that lives in every single one of these. Okay? And we're going to choose or pick that x to be the candidate for the limit of our subsequence. Okay, so we claim that this x is the limit of the subsequence A sub n k. All right, so we need to prove this. Okay, and we will prove this by thinking of the length of each one of these intervals. Okay, and what do I mean by that? Well, we started with our first interval, whichever side we chose, it went from 0 to m. So I sub 1 has length equal to m. So I will use absolute value here for length. Just bear with me on that. Okay. Then I sub 2, whichever one we choose, it's half the length of the previous. So it's going to be, its length will be m over 2. Then I sub 3 will be half of this length. So it will be m over 2, and then I'm going to multiply it by 1/2 again. So it will be m over 4 or m over 2 squared. Then I4 is going to be m over 2 to the third, and I'm talking about the length, and the length of, let's say, I5 will be half of this length, which will be m over 2 to the fourth. So the length of each I sub m is 1/2 the length of the previous interval. So the length of the interval I sub m will be m over 2 to the little m minus 1. Okay, well, how does this help us? And actually, it might be nicer if we said it was I sub m plus 1. Its length will just be m over 2 to the little m. Okay, that might look a little nicer. Okay, now the sequence 1 over 2 to the m converges to 0. So I'll say note that 1 over 2 to the m converges to 0 since 1/2 is greater than 1/2 squared, which is greater than 1/2 cubed, which is greater than 1/2 to the fourth, which is greater than 1/2 to the m, and all of these are greater than 0. So this sequence is bounded and monotone. So since I over 2 to the m is bounded and monotone, by the monotone convergence theorem, 1 over 2 to the m converges. Now, how do we know it converges to 0? Well, we can show it converges to 0 by thinking about its recursive formula. Right? Because if this, I'll call this B sub m, each B sub m, let's say plus 1, is the previous B sub m divided by 2. Okay? And if we suppose B sub m converges to capital B, then this statement, star, becomes, well, I'll have the limit of B sub m plus 1 is equal to the limit of B sub m over 2, which will give us capital B is equal to capital B over 2. And there's really only one possibility here. If we solve this equation, if I move this over, I get B halves is equal to 0, which tells me that B is 0. Okay, so this is true. Now, this seems like a real long walk, I know. However, because the length of each one of these intervals is m over 2 to some power, okay, we can actually utilize this. So, finally, for each m in the naturals, okay, a sub m and x are both in I sub m. Okay? Well, since they're both in I sub m, this means their distance, so I'll write this out. So the distance between a sub m and x is at least capital M over 2 to the m. And actually it's m minus 1 since we're in m here. Okay. Which if I wanted to change the way this looked, I could multiply the top and the bottom by 2 to get 2m over 2 to the little m. Okay, which maybe looks a little better. It's not really going to matter that much. So if their distance between a sub m and x is at least this, then for all little m in the naturals, we have that the absolute value of a sub m minus x is less than or equal to m over 2 to the m minus 1. Right? And this is for all m in the naturals. So, by exercise, I need to look it up here. It's 2 point, where'd it go? Here it is, 2.3.10. It's the one we looked at in a previous lecture that basically says if you can get the distance of the sequence, and I totally messed this up, didn't I? Okay, it's a sub m sub n sub m. Anyway, as the terms of all of the terms in the sequence minus the limit, if I can get it less than a sequence that converges to 0. So by example 2.3.10, since capital M over 2 to the m minus 1 converges to 0, A sub n sub m must converge to x. Okay, therefore, A sub n has a subsequence that converges to x. And that finishes the proof. So there's quite a few things that we had to take sort of side divergence. I had to diverge a little bit to actually prove a couple of things that we needed. However, the idea still holds that we keep splitting that interval in half, and we get smaller and smaller and smaller in the distance between the term that we grab out of each interval and this other element that we know has to be in all of those intervals by the nested interval property. We know that those distances are getting smaller and smaller and smaller, and the distance is getting smaller and smaller and smaller is exactly the definition of convergence. Okay, so what this gives us is, hey, if a sequence is bounded, that doesn't necessarily mean that the sequence itself converges. However, we can grab a subsequence from it that definitely does converge. Okay, so that is the nice thing that boundedness gives us. All right, I think that is definitely enough to throw at you in one video, so I will catch you all on the next one. Cheers.